Good evening, sir.
Good evening, sir.
Good evening.
Good evening, sir. Good evening, sir.
Our amateur astronomers are very excited today to know about sun.
Oh, wonderful. Wonderful.
Sir, we are so exciting to see you in the Zoom meeting.
I'm excited to see you too.
Thank you so much, sir.
I request all the students to keep their videos on and set the profile, the picture I have shared with you as your background picture, if it's possible for you, if you are comfortable with this technology.
And during the session, all the students will keep mic off, muted. Let us wait for another 2 minutes, then we will start. We have 18 participants.
Sure.
Yes.
Yeah, I'll try sharing my presentation here. So, is it visible?
Yes, it is visible.
All right.
So I think we should start now because then timely we can finish it up. So
Yeah.
on behalf, I am Professor Hemant Kumar, coordinator for NASNI. And for your information, NASNI is National Astronomy Network of IAPT. Is in the service to foster interest and engagement in astronomy and sky watching among students and teachers also, and in general public. And it is actually effort to bridge the gap between new sky gazers and experts by providing structured learning and mentorship, also the observational guidance in astronomy and astrophysics. It aims to nurture curiosity and promote scientific temper, also to connect enthusiasts with the leading astronomers and astrophysicists, and moreover, we say the experienced sky watchers also. So in this series now, today we have very experienced astrophysicist with us, Dr. Sarkar from IUCA, Tezpur University, Assam. And I remember Tezpur University was associated with the Aditya L1 mission also, and to contribute in solar ultraviolet imaging telescope also. So we are very curious to know more about it. We have with us Madam Tamanna from Rewari. She is the host of today's session. I will request Madam Tamanna to take over and introduce our very eminent speaker, Dr. Sarkar. Over to Tamanna.
Good evening to the entire NASNI club. I'm Tamanna Bansal, Physics Faculty Head of Department at RPS Group of Institutions. It gives me immense pleasure to welcome you all to 17th NASNI Talk with our esteemed speaker, Dr. Janmejoy Sarkar. Born and raised in Siliguri, West Bengal, Dr. Sarkar has been fascinated by night sky since childhood. His remarkable journey from an enthusiastic sky watcher to a scientist contributing to ISRO's frontline missions is truly inspiring for all of us. Today's session is especially significant as we are joined by a distinguished gathering of participants from bright young students of class 5 to 12 to eminent educators and scientists. Among us, we have the national coordinator of NASNI, Professor Hemant Kumar, and I think that Mr. P.K. Aluwalia, the president of IAPT, will be joining us very soon. We are truly privileged to welcome Dr. Sarkar, who will enlighten us on the fascinating topic, the sun from the space. And I'm confident that his insights will not only broaden our scientific understanding, but also spark curiosity and passion for astronomy in every listener present over here. So, ladies and gentlemen, please join me in extending a warm welcome to Dr. Janmejoy Sarkar. I'm sharing a virtual bouquet on the screen.
Thank you so much. Thank you so much.
Now we'll ask Upasna to introduce our speaker for today's talk.
Thank you so much, and everyone, all the dignitaries who are present in the Zoom meeting. It's my privilege to welcome our keynote speaker of this session today. Sir is a researcher in solar instrumentation and space science, currently associated with the Inter-University Center for Astronomy and Astrophysics and Tezpur University. Sir expertise lies in design, calibration, and operations of space-based optical payloads with a central role in the Solar Ultraviolet Imaging Telescope onboard Aditya L1, India's first solar mission. Sir has contributed extensively to payload integration, optical validation, contamination control, and satellite level testing at multiple ISRO centers. Following Aditya L1's launch, he continues to lead efforts in post-launch data calibration, performance monitoring, and payload operations. Dr. Sarkar's technical proficiency spans spectroscopy, optical metrology, vacuum systems, clean room operations, UV optics, CCD imaging, and payload qualification test. He is also skilled in Python programming, image processing, automation, and data pipeline development. His research achievements include multiple peer-reviewed publications in high-impact journals such as the Astrophysical Journal Letters, Solar Physics, and JATIS, focusing on suits design, calibration, and early solar observations. Sir has presented at major conferences, including the National Space Science Symposium, Astronomical Study of India meetings, and international forums. His contributions are actually received a lot of appreciations and achievements are like Distinguished Student Achiever Award from Tezpur University 2024, as the letter of appreciation from the Governor of Assam in 2023, and prestigious fellowships from IUCAA and ISRO. Beyond research, Sir actively engages in science outreach and education, serving as a resource person in ISRO and IUCAA workshops and training programs for students in education and educators. With a strong foundation in physics and astrophysics, he pursued his PhD from Tezpur University, MSc from Tezpur University, following and BSc from North Bengal University. Sir continues to advance India's capabilities. Moreover, I should say that Sir continues to advance Bharat's capabilities in space instrumentation and solar astrophysics. So we are truly privileged to have your guidance with all the young astronomers today. Thank you so much for coming and joining us.
Quite an introduction. Thank you so much, Upasna. And also to Professor Kumar and Madam Bansal. Also, I see Dr. Barua has joined, and Dr. Barua was actually my supervisor for my master's project. Also, where I worked very closely with him at Tezpur University Observatory. We made an instrument and had some wonderful results with that. Also, he's also more of a friend and less of a teacher, not only to me, also to all of us, all the students that we have. at Tezpur University. So it's very nice to see him. Thank you so much for having me. I'll quickly get to what I was here to talk about. And seeing that there is a huge crowd of school students, I believe everybody is from school or maybe college. So I was thinking of presenting a very formal conference-like presentation, thinking that this is the Indian Association of Physics Teachers. But then I thought that it's better to, see how the what kind of crowd I get. So let's go. I think we can start. So as the title says, the sun from space, India and the world. And the first thing that we discuss about is that why is the sun important to us? And please feel free to unmute your mic and ask questions or even respond to whatever I'm asking. Yeah, so that way we can have a good interaction. So the thing is that why is the sun important to us? Because you see, everything on the earth is kind of driven by the sun. The food that we eat, it comes from plants or maybe from animals who eat the plants, and that is powered by the sun. Some of the animals, they wake up and go to look for food when the sun is up. Some other animals, like this bat over here, wake up when the sun goes down and then goes to look for food. So practically everything, every animal, every plant is kind of driven by the sun. Similarly, you see, even it's not just animals who interact with the sun, it's also the plants. So on sea beaches, you might see this phenomenon of phototropism, where a tree grows towards the direction where it thinks that it can get more sunlight. Similarly with sunflowers, how sunflowers always keep looking at the sun, and that's why they're called sunflowers. And that's why you see, like, these are very small examples how the sun is directly ingrained in our day-to-day life. And the sun is so obvious. It's so obvious that we know that next tomorrow, when morning comes, the sun is going to rise. And it is so obvious to us that we kind of tend to not think about the sun. But here is the most important thing, that something that is so obvious and that is so closely related to our lives is the ones we should understand the best, right? And with that pursuit of understanding, we have been trying to figure out how the sun works and what the sun does to us for many decades, centuries, and millennia. There have been civilizations who have completely perished because of droughts, and there have been civilizations who have flourished because of fertility, and everything comes from the sun. So previously, when back in the day, nobody really understood how the sun worked, and everybody thought that probably worshipping the sun is going to make things easier for us, because agriculture was based on the sun. So all over the world, every single civilization has a god for the sun. So they made sun into a god and they would worship the sun. For example, this photograph that you see on screen, do you know which god this is? There is a chariot.
Sun god.
Yes, Surya Dev, exactly. From Indian mythology, Surya Dev, who has 7 horses, and then Surya Dev has a chariot which runs on one wheel. Yeah. And then you have, from Egyptian civilization, you have Ra, and then in Greek civilization you have Helios and Apollo. And then in the Mayan civilization you have a sun god, in Chinese civilization you have a sun god, and everywhere there has been a sun god from time to time, in every civilization. The reason behind that is sun gives us our food. Yeah, it gives us the paddy, it gives us rice, wheat, barley, whatever we want to eat. We grow it, and it grows because of the sun. And it's also because of the sun that crops don't flourish, because the sun is so bright in some situations that there is no proper wind flow, there is no proper fertility, and everything dries up, and the soil is not fertile anymore. We cannot grow anything. So the sun has been responsible for the rise and fall of civilizations. It is so important. And not only that, sun can also create very wonderful effects that you see over here. This is called an aurora. see these aurorae when near the North Pole or near the South Pole. Yeah? And also these beautiful colors in the sky that we see almost every day during a sunrise and sunset. When we say that, every sunrise or every sunset, it's a everyday phenomenon. We see a sunrise every day, we see a sunset every day. But then every sunrise is unique on its own, every sunset is unique on its own. You can't tell tomorrow's sunset is going to be the same as today. Every sunset and every sunrise is unique. And all of these beautiful things, these are happening because of the sun. Yeah. So as we progress in technology and as our civilization progresses, our need to study the sun increases even more, because now we are venturing into space. The last 50 years, last 70 years, there has been a huge exponential increase in the number of satellites in the sky, and our dependence to satellite communication and satellite-based services. So it's very necessary that we understand space very well when we're sending satellites. Just like back when Christopher Columbus was going out in the sea, it was very necessary to understand the seas and the oceans and the ocean currents and how do the winds flow, because back then people did not explore the seas as much, and then we were venturing into the seas for trade and commerce, and then we tried to understand the oceans and the seas and the sea currents and the winds even better. Same thing right now. This is the era when this is the age of space, and since we're sending so many satellites to space, so we need to understand the environment of space better. And for that to happen, we need to understand the sun better, because the reason is the Earth has a magnetic field, and the Earth has an atmosphere that kind of protects us from many different things, from charged particles, from these energetic particles coming from the sun, and but things in space are completely beyond that protection. So better predictive methods are required when to know that if anything adverse is going to happen to these satellites or not. For example, you might have come across these news like the solar storm. It destroyed 40 new SpaceX satellites. But this happened sometime last year, I believe, and that costed approximately $100 million of worth of loss. And then this person was very, very angry when that happened. And all of these things happen because we can't predict solar events as properly as we could. Also, an understanding of the sun is necessary to understand how weather works and how ocean currents work and how winds work on the Earth. Right? And it's not just the effect of sun lies only on the Earth. When you look at planets out there in the sky, you see Jupiter and then you see Saturn. You see these auroras happening on Jupiter and Saturn also. And that's very interesting because these planets have strong magnetic fields which kind of attract all the charged particles from the sun, and then they go and hit the atmosphere of these planets, and it causes these beautiful, colorful emissions. So you see how these aurorae, they happen in Jupiter as well as in Saturn. So as we are trying to go to other planets and trying to explore other planets, doing other interplanetary missions, it becomes more and more important to understand the interaction of the sun with other planets. Because when we send spacecrafts, when they go into the magnetic field of other planets, when they reach the gravitational attraction of other planets, then the interactions kind of change. So how the satellite interacts with solar charged particles is very different when it's close to a heavy planet than when it is in blank space. So these things become very important, and that's why it's necessary to understand how the sun interacts with even things in the interplanetary space. So just to give you a context as to how rapid or how frequent these events are. This is an event from May 2024. And it's not just May 2024. You see these solar flares and sunspots appearing on the sun every single day. It happens every single day. And you see there were these bunch of sunspots over here that appeared on 10th May 2024, which kind of flared. Suddenly they became bright. So just to give you a context, this is a view of the sun in one kind of telescope, and then you use a different kind of telescope to see this view of the sun, or the corona of the sun. Yeah. And that caused auroras to be seen all the way in Russia and Mongolia and in the US, where generally you don't see aurorae, because the number of charged particles that came out of the sun was so high that it caused a huge interaction near the poles of the Earth. And these events become very, very important, because even if you are not in space, it's very necessary to predict these events quickly, because there are these flights that fly over the poles. So let's say you are flying from Europe to the US. So if you looked at a globe, you would see Europe is on one side, and to the west you have USA. So on a map, you would think that it is a straight path from Europe to the USA. But actually, if you looked at the globe, you would see this is Europe over here. If you had to come to the USA along a straight path on the map, you would actually have to go around like this. Or let's say if you are coming from somewhere in Russia, let's say from Moscow, you wanted to fly to US. On a map, you would basically draw a line. So that would mean your kind of water path is going straight over the pole. Yeah, if you looked at the Earth, you would see that going from Russia to the US is easier to go. It's easier to go over the poles than to go around like this. Yeah, so that's the interesting thing. Now, let's just imagine you were in a flight going to the US at that time when the solar storm hit. It's a huge amount of radiation that you are getting exposed to. Yeah, and that has to be predicted beforehand, because these radiations are cancer causing. So although one radiation dose won't cause a huge harm, but then every person has kind of a threshold as to this much amount of radiation that they can take in one lifetime. And there are lots of people who keep flying on these, on the polar routes, who keep flying between Europe and the US for business. I mean, there are people who are flying almost every week or every month. For them, it becomes very risky, because if they are exposed to 2-3 such solar storms, then their chances of getting cancer becomes very, very high. Yeah. So that's why it's not just astronauts in space who are affected by the sun. It's also general people who are on the Earth and who are taking flights and who are living in these latitudes, who kind of also get exposed to these harmful radiation. Yeah. So the first study of one such energetic solar event, what we call a solar flare, was first recorded by Carrington and Hodgson back in 1859, when they both independently, with the two different telescopes, they kind of looked at the same group of sunspots. It was a huge sunspot. Kind of looked at the same group of sunspots. They drew it by hand, because back then nobody used to take photographs. People would draw what they see in the telescope. And then they saw the two regions on the sun were becoming very bright. And then that was the first documented indication of a solar flare, 1859. And after that, we have been fascinated by solar flares so much, because it's like the weather. We can't predict when it happens, but when it does happen, it causes, it has huge repercussions on the Earth. So these solar activity, it's not like that the sun is always risky. Okay, so the sun also has its own cycles. So there is some time when it's called solar minimum, when the sun is not active at all. If you looked at the sun, you would see that there are no sunspots on the sun. And if you looked at higher up in the sun's atmosphere, you would see that the sun looks pretty dull. But then 11 years later, when 5.5 years later, when the sun becomes very, very energetic, then you start seeing these sunspots. Yeah. And then the sun appears very bright in the upper atmosphere. That becomes very, very prominent. So yeah, so that becomes very interesting, that every 5.5 years the sun becomes really energetic, and the sun's energy again dies down after 5.5 years. Again, another 5.5 years later, the sun becomes very energetic. Again, after that, the sun slowly dies down. And it doesn't happen in one day. It takes time. It's like a gradual process. So, it's a gradual process. So as you can see, if you kind of counted the number of sunspots that you see every year, you see that every 5.5 years, there is a rise in the number of sunspots, and then there is a decrease in the number of sunspots. There is a rise and there is a decrease. And there was a time, sometime between 1650 and 1700, when the number of sunspots were very less. So the sun was behaving very, very, very unpredictably, and because that period is now called modern minimum, and that kind of matches with the mini ice age that the Earth saw during that time. That Europe and all these places, they were covered with ice throughout the year, which was which doesn't happen now or never happened before that. Yeah. So that is now. That being said, we say that the solar cycle is of 22 years, where basically every 11 years the sun comes back to its previous state. But even we don't know that for sure. That's kind of a pattern that we have found out, but we don't know how the next solar cycle is going to be, or how many sunspots are there going to be in the next solar cycle. And these things become PhD projects of various students to find out. It takes actually half a solar cycle's worth of work to predict what the next half of solar cycle is going to be. So it takes almost 5 years of PhD to predict what the next 5 years or next 10 years is going to be in the solar cycle. And then we will try to see whatever calculations that they have done, does it actually match with whatever predictions that they're putting out? Does it match with the observations in the next 5 or 10 years? So that's very interesting, because even with the current amount of science and current understanding and so many satellites and everything, we still don't understand some of the basic principles of the sun. And that's why we need to observe the sun more and more and more, because the sun is a star, and that's the only star that you can actually see. You can see stars in the sky though, but they're like points, they're dots. You can't make a telescope that can see stuff on a star. Sun is the only star that you can actually resolve, that you can see things happening on. No other star, even if you have the largest telescope in the world, even if you need a telescope the size of the Earth, even with that telescope, you cannot see what's happening on a star other than the sun. So the sun is kind of like a representative star. Sun kind of tells us. Understanding the sun also improves our understanding of how stars function in general. And understanding the sun helps us predict how the sun is going to behave in particular from time to time. Yeah? So speaking of the solar cycle, it kind of happens because of the twisting of the magnetic fields on the sun as the sun rotates. There's this thing called differential rotation, where the equator of the sun kind of moves faster than the poles of the sun. So it's like, if you had how do I put it? If you had a wet tennis ball, you take a tennis ball and you dip it in water, and then you spin it. So if you spin it, you will see that most of the water shoots out from the middle, and less water shoots out from the poles. That happens because the linear velocity at the poles is more than the linear velocity at the equator is more than the linear velocity at the poles. That's why the water shoots out from the poles much more than what happens on this thing. So the sun also behaves like that, because the sun it's not solid. It's not a solid ball of rock. Sun is a ball of glowing hot gas, what we call plasma. That's a fourth state of matter. Yeah, sun has a dense core, and then as you go up, it becomes softer and softer. But then it's still a ball of hot gas which behaves like a fluid, and then the center rotates faster than the poles. So if you looked at the sun, you would see that the sun has a pretty hot solid core with temperatures which are like few million degrees Celsius. And then there is this radiative zone where most of the heat that's generated in the sun, it comes out in the form of radiation. And then you have the convective zone where so in the radiative zone, the densities are very high, so it's kind of like solid. Okay, and then after that you have convective zone, which kind of behaves like liquid. How when you boil water, there are these convection currents that come up in a pot of boiling water. So when the bottom is hot and the top is cold, the water boils in a way that water from the bottom, because of its heat or because of its high energy, it comes up to the top, and the cold water from the top goes to the bottom. That's the convection, and you have convective currents in a pot of boiling water. Same thing that happens when happens in the sun in the convective zone. And on top of that, you have the solar atmosphere, which is kind of like air. It's not so dense, so it behaves like air. Yeah, it behaves like gas. And on top of that, you have the solar corona, which is very, 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 very less dense. The density is very less. So the main source of power in the sun is nuclear fusion. So there are two kinds of nuclear reactions that we know about. One is nuclear fission, where you have a heavy nucleus and you break it. For example, uranium. That's how nuclear power works. In a nuclear power plant, what you do is you hit a nucleus of uranium, and then you break it, and then it becomes two lighter nuclei, and it also releases some amount of energy. And then there is this other form of generating power. That is, if you take two light nuclei and under very special circumstances, you make them hit each other so hard that they fuse. Yeah, and when they fuse, they release a lot of energy, and that's called nuclear fusion. So when two hydrogen atoms, they come and, or rather, when you say hydrogen atoms, that's not true, because hydrogen atoms have one proton and one electron. But this is hydrogen atom without an electron, so we call a proton. So when two protons, they come and hit each other at very high speeds or such situation, then it releases a lot of power and also forms helium. Yeah? So when it releases a lot of power, that is what drives the sun. So there is light that's generated at the core over here. There are photons, gamma ray photons, very high energy photons that are generated over here. Now this photon keeps bouncing around, rather what scientific terms, what we say, scattering, or keeps getting absorbed and re-emitted, And as it comes out, it kind of starts losing energy. It's like a bouncing ball. If you had a ball and you hit it very hard, it would bounce a couple of times, but then eventually it would die out because it would lose energy. Same with these photons. So it keeps getting absorbed and re-emitted, and then by the time it reaches the surface of the sun, the temperature of the surface turns out to be approximately 5,000 degrees Celsius, while the center of the sun was million degrees Celsius. And it takes several thousands and thousands of years for these photons to actually come out to the surface of the sun. So the light that you are getting now from the sun was actually generated a few millions of years ago. So this light is very old light, which is a result of fusion reaction which happened a couple of million years ago. That light you're getting now. And currently, whatever fusion reaction is going on, that light, few million years later, Earth will get. Yeah, because inside the sun, the photon takes very long to come out from the core. So here's the interesting thing. Now, let's say, for example, you had an elephant, and there were 7 scientists who have never seen an elephant before, okay, or never heard of an elephant before, or they don't know of an elephant. So you tie their eyes, yeah, and you put them next to the elephant, and each of them is touching one part of the elephant. So if you ask each of them to explain, what would they say? So let's say, for example, there is this person who's touching the trunk of an elephant, and you ask them, what is an elephant like? And then the person says, an elephant is like a snake. Yeah, because they're touching only the trunk of the elephant, right? And then there is another person who's touching the tail of the elephant. You ask that person, what is an elephant like? And that person says, an elephant is like a rope. And then there is this person who is touching the ear of the elephant. And you ask that person, what is an elephant like? And that person says that an elephant is like a fan. None of them are right. Because an elephant is neither like a fan, nor like a snake, nor like a rope, right? But that is what is required for all of them to come together and discuss what they saw or what they felt. So when all of them, they come together and then they discuss and they put the pieces together, they come to this conclusion that there is a fan, there is a rope, there is a snake, there's a tree trunk, and then there is a wall. So probably an elephant might look like this. That's exactly what we do with the sun. You can't have one telescope that looks at everything of the sun. Yeah. So we make different telescopes to look at different parts of the sun. And how does that work? So let's say, for example, you see a sunrise or a sunset, right? So when you look at a sunset, sun looks like this. Yeah. Now, this is the sun in visible light. You see all the colors of the sun that your eyes can see. Yeah. Now, what we do is we select specific wavelengths of the sun, because we know from calculations, we have found out that different layers of the sun, different electronic transitions. So basically, there are specific elements at different heights, or rather, how do I put it? There are favored electronic transitions. So that means at certain temperatures and at certain pressures in the Earth, in the sun's atmosphere, some lights, the generation of sunlight, some colors of light is favored. So there are some that kind of get generated at certain heights in the sun's atmosphere. Okay, so at the lower heights, there are certain wavelengths that get generated, and at the higher atmosphere, there are certain wavelengths that get generated. So if you looked at the sun in those specific wavelengths, you can get different views of the sun. So you see how the sun appears very different in these different bands of light, and there is each band is actually represents different heights in the sun's atmosphere. That's why we need multiple telescopes, and each telescope can't work on its own. So you need to have coordinated observations. So you have to have all these telescopes working together just to understand the sun and how it functions. Yeah. So that's the interesting thing, that it's not possible for one country or for one person or for one institution to do all this study. It's not possible. That's why we have these international efforts from different countries, from different organizations, different teams, different groups, who study or who look at different heights in the sun's atmosphere. Yeah. And then they communicate with each other and try to find out how the sun actually works. So there are different instruments. For example, some of the most popularly used instruments, or some of the most popular, or what do you say? Some of the most remarkable instruments that have been very successful till date. There's one SOHO that was launched in 1995, and SOHO is specialized for observing the corona of the sun, the outer corona. You see these streamers. Yeah. You see these streamers and jets coming out of the sun. And then you have the Solar Dynamics Observatory, where there are 4 different telescopes, actually 5 telescopes, who look at the sun's different heights and sun's magnetic field and everything. And you get images like these that shows the sun's lower corona. So this gives upper corona. Who look at very small regions of the sun with very high resolution and with very high detail. So you see how this telescope looks at the whole sun, while this telescope looks at a very small portion of the sun, but with very fine detail, with very high amount of detail. So the functions for each telescope is very different, but then all of them, when put together, can give very good scientific results. So like I said, you have these different instruments who look at different layers of the sun's atmosphere. And one such contribution has recently been flown from India.
Excuse me.
That is called the Aditya L1 mission.
Excuse me, sir.
Yeah.
Sir, could you please explain the previous slide where you showed the sun and different filters? No, the next one. The next.
Is this
next,
the one?
Next one, where you showed the sun and different filters. The next one.
This?
Yes, yeah.
Oh, okay, yeah. So that's what I was saying. So this is a cutout from this instrument, SDO, Solar Dynamics Observatory. So there is this, you see these 4 telescopes on the top of the satellite. So each of these 4 telescopes have 2 channels each. So these 4 telescopes all together, they take photos of 8 different layers of the sun's atmosphere. Each telescope is responsible for photographing 2 of them. So I cannot put all 8 over here. I have shown only 4. So this is just to show how the sun looks so different from one layer to the other. So if you looked at it, you see this one at the bottom right, AISC 160 nanometers, how this layer kind of looks like the surface of a planet. But this layer on the left hand side, 19.3 nanometers, that looks very gaseous, right?
Yeah.
It looks as if it's filled with gas. Yeah, that's because we are gradually going from lower atmosphere to higher atmosphere. So you see, this is, if you said in terms of levels, this is level 1, then you have level 2, then you have level 3, and then you have level 4. Yeah, so gradually 160 nanometers, and then 30 nanometers, then 17 nanometers, and then 193 nanometers. So you go from the bottom to the top. Yeah? And as you go to the top, it becomes more and more gaseous. You see how this one, 304, it looks kind of like a liquid.
Yeah.
Yeah, these flows, they look kind of liquid-like. And you can also look at these images. There is this, the data from this website, it comes in they have a very beautiful interface for students as well as for teachers and scientists. That's called HelioViewer. So you can look that up, HelioViewer, and you can actually show, it can play movies of the sun from the last couple of hours, and you can select a particular time and see each of these channels, how the sun looks in them. Yeah. All right. So the contribution from India was the Aditya L1 mission, where India sent a spacecraft to the Lagrange 1 point of the Sun Earth. So Lagrange 1 is this really interesting point, this kind of position between the Sun and the Earth. It's just 1% closer to the Sun. The Sun is 150 million kilometers away. This Lagrange 1 point is 1.5 million kilometers away from the Earth. But still, 1.5 million kilometers is actually 4 times the distance of Moon. The spacecraft actually is very far away from the Earth. Yeah, and the advantage of this location is that you can keep going around the Sun like a planet. Yeah, there is this joint gravitational attraction of the Earth and the Sun, which kind of balances the amount of gravity that's required for an object at this position to keep going around the Sun like a planet with the same period as that of Earth. So Earth makes one orbit in 365 days. L1 point also makes an orbit of 365 days. So if you keep something at L1, it can keep going around with the Earth. Yeah. And the advantage is, if you had a satellite, the satellite can sometimes fall behind the shadow of the Earth. So a satellite is going around the Earth. So there are specialized orbits which you use to constantly observe the Sun. But then that's called the Sun synchronous orbit and all that. But then in such situations also, the satellite does fall into the shadow of the Earth at times. But if you kept something at the Lagrange 1, there is no chance of that happening. So you constantly can keep looking at the Sun 24/7. So that's what we need. So in Aditya L1, there are different instruments. There are 2 telescopes called VELC and SUIT. And then there are 2 X-ray spectrometers, which basically look at the Sun in X-ray. They don't take photos. They measure the total amount of X-ray radiation coming from the Sun. Then that's Solex and Helios. And then there are these particle detectors that detects what kind of charged particles are coming from the Sun. That's called Aspects and PAPA. And finally, there is another instrument that's called a magnetometer, because it basically measures the amount of magnetic field that's there at the Lagrange 1 point. This is Aditya L1. And the instrument that I worked on, that I helped build, is called the Solar Ultraviolet Imaging Telescope, SUIT. So SUIT has 11 channels. So we look at the Sun in 11 channels. Among them, there are 3 channels which kind of look at the Sun in the ultraviolet A, ultraviolet B, ultraviolet C. That's very necessary to understand the chemistry, how the sunlight, how UV radiation affects the chemistry of Earth's atmosphere. So this is SUIT from the inside, and this is a schematic drawing of SUIT, where the light comes like this and it hits a mirror, and then there's another mirror. Then there are these filters that kind of help in selecting the correct band of light, and then it goes and hits the CCD, or basically the camera that helps in taking the photos. Yeah. So this is me with SUIT. This photo I put here to give you a size of, to give you an idea of the size, how big the instrument is. It's 1.5 1.1 meters long, around 30 centimeters wide. Yeah. And this is the spacecraft where this is suit mounted on top over here. This is the Aditya L1 spacecraft while we were integrating the spacecraft in the lab. Yeah. So, like I said, now this part could be a little bit technical. That is the spectrum of the sun. So, sun is kind of has a similar energy levels or similar brightness at the shorter wavelengths. That is, in extreme ultraviolet and ultraviolet, it kind of has more or less the same energy level. But then you see how the brightness of the sun suddenly increases between 200 nanometers and 400 nanometers. In this region, the brightness of the sun, it suddenly increases. That's why you need very specialized telescopes to observe this part, because if you make a telescope to look at this light of the sun, then this part becomes very bright. If you make a telescope to observe this part, then this part becomes very dim. So you need to have a telescope that can encompass this entire range and take photos properly. And that's where we come in, because no other organization had built a telescope who could build a telescope which can accommodate this huge difference or a huge change in the brightness of the sun with change in wavelength. But then that's why we came in and we made this instrument called SUIT, which takes the sun's observations from 200 nanometers to 400 nanometers. There was one instrument that's called IRIS, but then IRIS takes very small pictures of very small regions on the sun. For example, this one. Yeah. So this box that you see over here, that is actually this tiny box on the entire sun. So you don't get a view of the entire sun. And then we came in and we made SUIT, which gives you the view of the entire sun. So now you see how you look at the sun in ultraviolet as a whole. So with this instrument IRIS, you get very high resolution, sharp images for small regions of the sun. While our telescope, it gives you the view of the entire sun. And nobody has done this before. We are the first country in the world to make a telescope which looks at the sun in near ultraviolet and looks at the entire disk of the sun in one go. So, like I said, along with that, the biggest advantage is, since we are at the Lagrange 1 point, we always keep looking at the sun. There is no down. That's another big advantage that we have. So, like I said, SUIT has 11 different channels in which we look at the sun. Two of the most interesting ones are these and these. So these are two interesting channels because they are what the sun looks like due to emissions of magnesium line emissions. These are what the sun looks like due to emissions of magnesium. See, the sun is filled with hydrogen. Okay, so the most of the radiation that you see, that we use telescopes to see, are mostly coming from hydrogen. But then there are also these elements which are in very sparse quantities, but they also emit light. So we filter out every other light and we look only those specific bands which are necessary emission from these specific elements. So along with that, we have this observation mode in which we pick out only one small region of the sun and look at that region at very high pace, very high cadence. Along with that, we have a capability to predict a solar flare. So there are these extra spectrometers on Aditya, the Solex and Helios that I said. We use the data from that instrument. And then we also have onboard intelligence algorithms that can predict when a solar flare will happen. And then automatically it changes its observation mode, finds out when the solar flare could happen, it locks onto that position and starts taking images. So we are also the first telescope who has the capability to study flare emergence. Means before a flare happens, we can tell, only a couple of minutes before a flare hits, we can tell that a flare is going to happen and we start taking images of that. So this is one such thing where you see how we started taking photos before the flare had even started. That is a very interesting thing. Yeah. So coming to this, Now, like I said, it's not possible for only one instrument to observe the sun. Previously we had missions like Solar Dynamics Observatory in space, like IRIS in space, like SOHO in space. But these are old missions. The last big mission was, I think, 12, 13 years ago. Yeah. And then the next remarkable mission that happened was Aditya L1. And we are now in service, and we are taking these wonderful images of the sun and doing this science, studying new things in the sun which nobody had seen before. Yeah. And it's not the end. This is the beginning, because Aditya L1 is the one which went from the Earth to Lagrange 1 point, and it's going around the Lagrange 1 point. Then you have Solar Orbiter. This is another mission that was flown a couple of years back. And Solar Orbiter, like the name says, it orbits the sun, and does not only orbit the sun in one direction. As it orbits, it is tilting its orbit to look at the poles of the sun, the North Pole and the South Pole of the sun, that nobody has seen before. So for the very first time, we're using the spacecraft to go around the sun like this vertically. Everybody till date, we have always observed the sun face on. Yeah, we have never seen the top and the bottom of the sun. This is our first opportunity to see the top and the bottom of the sun, what they actually look like. Yeah. Then you have the Parker Solar Probe, which basically went and kissed the sun and came back. Yeah, and it's constantly doing that, because it's like it goes very close to the sun and then it goes very far away, highly elliptical orbit, and then it again goes very close to the sun and very far away. So when you go very close to the sun, you see how the local magnetic field over there is, how the charged particles over there is, what the sun actually looks like in very high resolution. Yeah, how the streamers from the sun emerge, these things. Yeah. And then you have Proba 3, which is the first example of coordinated flying. So coordinated flying means two telescopes in sky fly with each other. Yeah. So you have one satellite over here, which is basically an occulter. Occulter means it will block the sunlight. Yeah. And then another telescope which takes photo from behind. So when you block the sunlight, what happens is you block the disk of the sun, and then you can see everything that is outside the corona of the sun. Yeah. So you need to see that, and this is the first example where, just imagine, in space we are doing this, where we use one satellite to block the sun, and then from far away we put another satellite in alignment so that both of them are moving and orbiting around the Earth. While doing that, we click photos of the sun while blocking the disk of the sun and taking photos of the corona. And you would be surprised to know, this Proba 3 mission, such a sensitive mission, our PSLV was used to launch this mission. This is a European Space Agency mission, but then the launch was done by ISRO over here. Yeah? So this is what happens. You have one telescope, and then you have the occulter satellite, which blocks the sun, and you have the imaging telescope, which takes photo from behind, and you get this view of the sun where you can see the solar corona. So this is a recent image of a current orbit of solar orbiter, where you see the bottom of the sun, South Pole. Yeah. And then this is the image from Proba 3, where you use one satellite to block the sun and another satellite to take photo of the corona. The most detailed view of corona ever. Yeah. And then you have Solar Orbiter, which went very close to the sun, and you see these streamers coming out from the sun from at such close vicinity. And why these are necessary is because you see all these instruments, they are at different positions in the sky. Yeah, when you look at the sun, anything that happens on the sun, it appears like 2D, like two-dimensional. You don't know the geometry of structures. Yeah, but if you had the same observation from two different places, then you can figure out the geometry, how big a loop is on the sun, or how far a coronal mass ejection is going, or how fast it is going. It becomes very easy to do these calculations. Yeah, so that's why when the times are favorable, the Solar Orbiter team, they coordinated with us, and we looked at the sun simultaneously. When Solar Orbiter was on one side of the sun and we are at Lagrange 1, and we had some wonderful results from that. Same with Parker Solar Probe, we have these observations. Same with IRIS mission, we have we regularly plan these joint observations where we both look at the same region of the sun from different vantage points, from different wavelengths, at different time cadences, at different resolutions, to extract as much science as possible. It is exactly like all the scientists coming together and talking to each other, trying to figure out what the elephant actually looks like. So that is all from me. Thank you so much, and I encourage all of you to be interested in the sun, because I see many students and many scientists who are very interested in black holes and in pulsars and these transient objects in the sky, blazars, galaxies. Yeah, but then the sun is like it's like our closest neighbor, and we know so little about the sun, even though it drives everything around us. Yeah, so we need more and more young people like you to grow up and study about the sun and do research so that you can find new things about the sun. Because the more we know about the sun, the more we realize that we don't know the sun at all. That's the most interesting thing about the sun. It's like a running enigma. Nobody really knows what the sun is. And if we don't know, it's a
Sir, 91% hydrogen and sir 8.9 helium gas make up the sun.
Yes, that is true. That is true.
And sir, the temperature of core is 15 million Celsius.
Exactly. Yeah. The core is very hot, and you would be surprised to know that it's not only the core that's hot. So as you come from the core and you go to the surface of the sun, the core is 15 million degrees Celsius, and the surface of the sun is 5,000 degrees Celsius only. But then you go to the corona, that's 1 million degrees Celsius. So you would expect, if you had a candle, if you touch the candle, it would be hot. And then you keep going away from the candle, it would get cooler and cooler and cooler. But in the sun, after you leave the surface of the sun, things start getting hot again. And that's a big open question. Nobody really knows why that happens. So that is also another question that everybody is trying to answer. That this part of the sun, this corona, this is few million degrees Celsius, even though it's so far out from the sun, and nobody knows why. Yeah, that's called the coronal heating problem. There's a name to it, coronal heating problem. Nobody knows why this is happening. Everybody's trying to figure out why.
Dr. Sarkar, these students know that how much time light takes from sun to earth. That is about 8 minutes or 20 seconds. But please revise, tell them again that how much time a photon takes from center to come on the surface of earth. Sun, sorry.
Yeah. Mm-hmm. Yes, so that is very interesting.
To travel 14 lakh kilometers, how much time it takes?
Exactly. That is very interesting. Thank you for pointing it out, Professor Kumar. That is the sun, light from the sun that we see, that light comes from the surface of the sun. That's called the photosphere of the sun. And that light travels 150 million kilometers to Earth within just 8 minutes and 20 seconds. Yeah. But the light that is generated inside the sun, it is generated in the core, which is 15 million degrees Celsius. So that light takes a couple of million years, thousands and thousands of years, just to come to the surface. Because the inside of the sun is so dense that the photon that's generated inside does not get enough space to come out. It's like getting in a local train. Yeah. So if you can run, let's say you can run very fast. If you have an open field, you can run very fast. You can run from your home to the playground, or you can run from the playground to the home very quickly. But let's say you're inside a very crowded local train, yeah, or you're inside a very crowded bus. You can't even walk. The bus is so crowded. You would have to keep pushing people around, keep going around, and then other people will push you. Then you have to push other people, and it's going to take you so much longer just to come to the door of the sun, just to come to the door of the bus. But once you reach the door of the bus, after that it's empty. And then you run, you cross the field, you run and you reach home. So it takes you the same amount of time, or it takes you much shorter to travel 150 million kilometers, but takes you so much longer just to travel from the core of the sun to the surface of the sun. Because inside it's very crowded. The photon does not get space to come out.
Sir, the Earth is made to sir, some elements like sir, nitrogen and carbon.
Yes. I didn't understand what he wanted to ask.
Sir, sir, many elements make up the sun, sir, like nitrogen and carbon.
Oh, yeah. Sun also does have nitrogen and carbon. Sun also has magnesium. Sun also has calcium, silicon. Lots of elements are there. But they are in very small quantities. Like you said, most of it is hydrogen, and then you have helium, and then everything else you have in try to observe the things that we can't generally see. We make specialized telescopes to observe those special elements on the sun. So with SUIT and with these instruments, we are trying to observe magnesium and how magnesium interacts with everything else.
Sir, I would like to ask something.
Yes.
So I'm Amoli Kakkar from Jaipur, and I have been a regular sun observer. I have a data of about 3 years to collect the number of sunspots and the sun groups. I've been doing it regularly. So here we are talking about a star, the sun. I have heard that there are some emission stars and there are some absorption stars.
Right.
So what's the difference between an emission star and an absorption star? How does a star absorb?
Okay. That's a very wonderful question, actually. And I really congratulate you for collecting data. And are you observing with your own telescope, or do you?
Yes, sir. I have a Celestron 8-inch and a solar filter, a normal regular solar filter.
Yeah.
And I observe doing that.
That's very nice. And I mean, it's very nice to see so many enthusiastic people who are into astronomy and who do it just for the sake of doing it, for the love of it.
So, but I really want to do some science out of it. What can I do by particular data?
I understand. Yes. There is a. I mean, the data that you are collecting right now, it's very useful in many different ways. So, answering your first question, absorption star and emission star, some stars, or rather most stars, have an atmosphere, right? So since you have an atmosphere, like say for example the sun, you have the photosphere of the sun underneath, and then you have the chromosphere and the corona of the sun. So the photosphere, what it does is it releases a wide band of light, almost every wavelength it's releasing, yeah. And then there is the atmosphere, which has abundance of different gases. They kind of get excited with the light that's coming from the photosphere. For example, hydrogen gets excited, and the electrons, they jump from second orbit to third orbit, yeah. And that happens when you absorb lights of around 656 nanometers. That's the one we call H alpha, yeah. So the hydrogen atoms, they absorb H alpha and H beta lines, and then they have these transitions. So if you looked at the sun from the earth, what you would see is that you have all the light, but then 656 nanometer light is less.
Okay.
So that is the absorption. And it's not just hydrogen alpha and beta. All the other elements, they do that. And it's not only that, these elements, after they absorb the light, they also re-emit it. So if you took a hydrogen alpha telescope and you looked at the sun, you would be looking at the re-emission of that light.
Okay, so the H alpha filters shows us the re-emission of the hydrogen lines.
Exactly. Yes.
Okay.
So if you did spectroscopy of the sun, you would notice that you are looking at the entire spectrum, and then you have these absorption lines on it, because the intensity of H alpha that's coming from re-emission is much lesser than the intensity of the total sunlight coming. So when you do spectroscopy, you would see a dip at H alpha, But if you took a H alpha telescope specifically and looked at that specific wavelength, you would see this thing.
Emissions.
You would see the emission from the atmosphere. So this is basically absorption star. And then there are these special types of stars which are called Wolf-Rayet stars, and there are some other stars which are in some phase of their life cycle where they tend to emit a lot of light in specific wavelengths. And if you looked at these Wolf-Rayet stars, their spectra, they would see that there are peaks at certain specific wavelengths. They have a continua emission, and instead of absorptions, they have peaks. So these are like the emission stars.
So our star is basically an absorption star.
Yes. Yeah.
Okay. So, sir, the prominences which we see,
Yeah.
are they the H alpha emissions, re-emissions?
Yeah. So prominences are basically clouds of gas.
Yeah.
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 So these prominences, we call them prominence when they appear on the edge.
Yeah.
So if this is the ball, and there is a cloud on the side,
yeah,
we call that a prominence. But if the cloud is in front, we call that a filament.
Okay.
Yeah, so filament, they look like filaments basically, like snake-like structures on the sun.
Yeah.
On the chromosphere. So we call them filaments if they are on the front, and if that same filament from the disk of the sun, if it's on the side, then you can actually see it from here, and then you call them a prominence. So these,
yeah. One more thing.
Please.
Sir, during the total solar eclipse, when we see the corona, the red thing, the red filaments which are coming out. So what are that?
Yeah. So have you seen a total solar eclipse?
Yes, sir.
Very beautiful. Yeah. Very nice. So
I've recorded annular solar eclipse which happened in India in 2020.
Oh yeah, the 2020 eclipse. I missed that eclipse because of COVID. We had to cancel our flights and everything.
Yeah, I know that. We went in COVID to from Jaipur to Suratgarh to just shoot that eclipse.
That was almost, I think, 90% plus occultation.
Very thin. It was 94%. 94%.
Exactly. Yes. I remember.
Yes.
It was very, very high occultation eclipse. Yes.
Yeah.
For total solar eclipse, what happens is you see the chromosphere, the red stuff that you see the chromosphere, and there's a reason why it was called chromosphere, and it was not called something that's red. Chromos means color, right? So the chromosphere has emission which is hydrogen alpha and hydrogen beta. Hydrogen beta is green, hydrogen alpha is red. So these two together look very beautiful during a total solar eclipse.
Okay.
It appears mostly red, but there is also some green to it. And that's why people named it chromosphere, because that was the first time when people saw the most prominent thing is the corona during totality. And then you can see this red ring around it. But if you looked closely during totality, you would realize that it's not just red. There is also green in it, like some amount of blue, 480 nanometers approximately, some amount of blue in it. So it's kind of like blue and red kind of thing. So that's H alpha and H beta together.
Okay. Yeah. So one more thing. I have a habit of observing the sunset because it's easily visible from my balcony.
Yeah.
So during sunset, very recently, about a month or so, around a month back, while the sun was setting, I saw a very light green hue on it.
Yeah.
Just for a second or hardly 2 seconds.
Yeah.
And before I could get my phone, it was gone. So what was that? I was so excited, and I tried to see it again, but I never saw it.
Yeah. So the phenomenon that you have seen, it's called a green flash. It's not common at all. You see, it's very rare to get to see it, especially in today's scenario, because to see a green flash, you would have to have very clean air.
Yeah.
And you would have to have a situation where there is very little light scattering happening at low altitudes. So, so it happens because of the stratified layer of Earth's atmosphere. When green flash happens, the sun has already set, and then that's a refracted light of the sun that you see. Yeah, that light is bending and coming to you, and because of interactions with the atmosphere, and I'm not remembering the exact reason for that, it kind of appears like the disk, and then there is some portion of the disk which is cut and come on top, which appears green.
Yes.
So green flash is mostly visible from places where the atmosphere is very, very clean. Yeah. So generally, people who see green flashes, they are kind of, situated on the west coast of some country or somewhere where, there is a sea and there is an ocean beyond that, and the atmosphere is really stable over there. Or there are people like the pilots who are flying west on an aeroplane. They can see a green flash for very long if the sky is very clear and if they're lucky. Yeah. But then seeing it from the middle of a city, I mean, seeing it from Jaipur itself is a big thing. I mean, it's very, very rare. So you have actually witnessed something which very few people in the world get to see. I have never seen a green flash.
In that way, I'm lucky. And sir, what about what to do about the data for the sunspots which I have? What can I do?
Exactly, data for the sunspots. So there are three things that you can do. First thing is you can make all the data, whatever data that you have. First thing is if it's scientific data, you should not keep it with yourself. You just share it with everyone. That is the first thing. Second thing is that generally this sunspot photosphere data, that's being recorded by many space-based and ground-based observatories. Yeah. So this data by itself is, I mean, if you wanted to do science with it, right? If a scientist wanted to do science with it, or if you wanted to do science with it, I would always insist that you use data from an observatory. From a recognized observatory who are already producing these data products, because obviously the data that you are recording is through varying atmospheric conditions, and then but then there's the same photospheric data that is being recorded from space. So the atmosphere is very stable over there. Yeah. So these things are there. But that being said, what you can do is you can try to calibrate the data that you have. What calibration means is that, the usual dark bias flat subtraction and these things. And after that, the implementation of coordinate system to those images. So let's say you are recording these images with a astro camera or with a CCD or with a DSLR. Yeah. So the first thing would be, if you're recording it with an astro camera, then you are probably getting FITS files, FITS, FITS images, or else you are recording them as photographs with your DSLR or with some camera.
So I do it with my mobile phone.
Or with the phone.
I keep it on the telescope eyepiece, and then I click the pictures.
Okay.
Sometimes if the sky is not so clear, it's partially cloudy, then I just count the sunspots and the sun groups and just record it.
Yeah. So in that situation, what you can do is you can make a catalog of whatever you're observing and put it on a website.
So I send it to AFSO. I send it there.
I understand, but AFSO is, it's a variable star observers. There's the American Association of Variable Star Observers.
They actually do the solar observations also, and they have the record for that also.
Okay, well, that's very good.
Sarkar,
Then that's
Madam, Dr. Sarkar, Madam Amoli is a citizen scientist.
Yeah.
And she is doing wonderful work in citizen science also.
That's
so
very nice.
I have shared your number to Madam, and you can have good discussion.
Sure.
Yeah, I'll definitely connect with you, sir.
Yeah.
So we can give chance to few students also who want to ask some questions.
Sir. Thank you. I'm really sorry for the time, sir.
No issue. Thank you so much. Students are connected. Actually, they want to ask some questions.
Sure, sir.
Students, you are welcome to ask questions from Dr. Sarkar. Yes.
Sir, I have a question.
Yes, go ahead.
So how do we actually count sunspots, and can we do it with our naked eye, or do we buy some satellite kind of thing and then observe them?
Okay,
Yes.
so it's a good question. Um, Previously, back in the day when cameras were not really available, then people used to count sunspots by eye. So you look through an eyepiece in a telescope and you count how many sunspots are there. But then with time, as data keeping became more and more efficient and we have the provision for images, people started taking photographs. And then there were these observers who would take photographs and the scientists who would later, count the sunspots and make a catalog out of that. But now we have computer vision techniques. We don't do these things by eye anymore. We have computers which can count how many sunspots are there and then put it in a list. So presently, sunspot counting in particular has become very, very automated.
We have Dr. Vandana Luthra from Gargi College, Delhi. Madam, do you want to interact with Dr. Sarkar?
Sir, I have doubt.
Yes,
Sir,
go ahead.
sir, what will happen if when is sun disappear from space?
Okay, good question. Yeah. So if the sun disappears from space, there are short-term problems and long-term problems. Yeah. Short-term problem is you'll start feeling cold. First thing is tomorrow when you wake up, you won't see sun is there. Yeah, that's the short-term problem. And then we'll start feeling cold because obviously, the atmosphere can only hold so much amount of heat by the greenhouse effect. Then we'll start feeling cold. Then suddenly there will be an ice age. And everything will become very, very cold. Number one. Number two is, this is considering that the sun has stopped glowing. Considering that the sun has disappeared, like gone, vanished, then everything will get scattered because we are all roaming, going around the sun because of the gravity. Yeah. So suddenly, if the sun goes away, we will all shoot out in one particular direction because there is this gravity going. It's like, how you take a rock and tie it to a rope and you spin it and then you suddenly leave it. What happens to the rock? It shoots out in one direction, right? That's what's going to happen. Suddenly the sun stopped being there. All the planets would just shoot out in one particular direction. That's the first thing that will happen. Yeah.
May I go ahead, sir?
Yes, Yashika.
It's a very big pleasure for us students to have such an erudite person like you. I apologize initially only to go off the topic, but I wanted to discuss a very interest-seeking topic, which is so fascinating for me. I want you to share your opinion on that. Could the universe be conscious, like consciousness of universe?
Mm-hmm. Well, yeah, that's very philosophical. Good question. Consciousness. Can I ask you something? Since you asked this question, how do you know that you are conscious?
There are certain things like we respond. If there is any stimuli in the environment, we respond to that. There are certain activities which goes through us,
Mm-hmm.
like which makes us feel like that we are conscious.
Mm-hmm.
Like we are science students, so we know that we are conscious.
Exactly. So, if I asked you about a plant like, touch me not, touch me not, right?
Yes, sir.
Or a Venus flytrap, do you
Yes.
think that a touch me not or a Venus flytrap is conscious? I'm asking you these questions just so I get to understand, so that I can calibrate my understanding with yours of what you mean by consciousness.
So they respond to the moment. Like if we talk about touch me plant, then if we touch that, that responds to that movement. That shows tropism. That in plants and Venus flytraps, whenever an insect enters it, it shuts down. Means basically it closes. And apart from that, plant also show many moments which makes us feel that they are conscious. Like they
Okay.
make their own food. They
Mm-hmm.
respond. There are various tropism movements in them.
Mm-hmm. Okay, that's good. So let's just say that all these things are happening within us because of electrical impulses going on in our nervous system, right? In plants, it's happening because of several hormones flowing from one place to another place that causes these tropism, like auxin and cytokinin and these things flowing from place to place that causes the movements in plants and how they respond to these external stimuli. So if you looked at the sky in space, you would recognize or you would realize that under with at very large time scales, the sky also responds to stimuli. Yeah. So, for example, if there is a comet passing by and it reaches near the sun, it gets attracted to the sun. And when the sun heats it up, the ice melts and it becomes cloud. Yeah. And then that comet leaves a trail of dust and gas, and then it goes away and freezes again. So, if you consider plants as being conscious, then I can't argue that the universe is not. Right?
We can come up with few more queries from the students.
Yeah, I have a small question, Dr. Sarkar.
Yes, sir.
The data you're receiving from Aditya L1, can all those data can be used by the common people, like the social scientists, or by the other countries also?
Yeah. So absolutely, that is something I want to encourage over here. Any person, be it someone from India, someone from abroad, someone who is a citizen scientist, someone who is an amateur astronomer, a professional astronomer, anyone can download the data for free from ISRO's website. So there is the ISRO Pradhan, PRADAN, the Pradhan portal of ISRO. You have to make an account with your email ID over there. When you log in, you can download all the data, not only from Aditya, not only from Suit that we are recording. All the instruments of Aditya, you can download the data. All the instruments from Chandrayaan, you can download the data. So all the photos that were taken by Chandrayaan, you can even download that data. If you want to do any science, you can do science. This data you can process. If you know image processing and if you like to do image processing, then anyone can process those images and use them for non-commercial purposes, for educational purposes. Use them for making, merchandise. You can print them on T-shirts. You can, or you can do scientific work if you want to. You can make posters out of them, and that's actually encouraged. But the thing is, wherever you use the data, you will see that there is a data usage guideline, which is just one line where you have to write that this data is provided by this institution, and it's just that credit line you have to add. That's it. Other than that, the data is freely available for everyone to use.
And to analyze all this data, can we use any specific programming or the software?
Okay, so it completely depends on the kind of work someone wants to do. So there are people who are working in machine learning who are using this data to develop new machine learning methods for their computer science students who are using new machine learning methods to look for features on the sun. Like a student asked some time back that about counting sunspots. So counting sunspots is fairly simple, but then there are other complicated features in the sun, like Amoli madam was saying about these solar filaments and these things, which are tough to detect at times. So you use these computer vision methods to detect. So it's not just solar physicists who are using this data. There are computer scientists and other people from machine learning who are also using this data. And then we have other uses for example, there are these other missions coming up, like the Venus mission, like the Shukrayaan mission. For these, we want to observe the sun in ultraviolet and understand how the sun behaves in ultraviolet, so that a couple of years later, when we send Shukrayaan and we do a hyperspectral imaging of Venus in ultraviolet, so that we know how it's going to respond to sunlight. Yeah, so that is also important. On the other side, I actually know people who are making mouse pads and these mobile covers with the images that we have taken using Suit. So these images are also there. So you can either download the data, process them however you want. If you want to do scientific work, then there are these codes that lots of people use depending on the use cases in IDL or in Python or somewhere. Or if you are more of a photographer, you can process them in PixInsight or in, say, your Photoshop or somewhere, and then you can use it for whatever purpose you want. Also, the prepared good-looking images, they're also available on our website. It's suit.iuka.in. So if you want to look at those photographs, we are still in the process of improving our image processing software so that we get cleaner and better images. But whatever results we have right now, you can download them from our website.
Okay, thank you very much.
Thank you, sir.
We have another question from S. Patel. Dr. Sarkar, we have question from S. Patel.
Yes.
S. Patel, please go ahead with the question. Then we have one more question from Tilk Sharma.
Yes. Hello, sir. I'm
Yes.
Shahavir. I had a curious question. Like, what if the sun was flat?
Mm-hmm.
So what would happen?
Couple of considerations over here. Since you asked a question, I would encourage you to tell me, how is it flat? Is it flat like this, or is it flat like this? Or is it flat like this?
Horizontal.
Horizontal. You mean like this?
It's horizontal. Horizontal, yes.
Like this or like this?
S. Patel, switch on your camera also.
1 minute.
Like this.
Yes.
Like this, yeah. So just think about it. If the sun were like this, then all the light would go to the top and to the bottom, right? And then you have all these planets going around like this, around the ecliptic. Yeah. So none of the planets would get any light at first. They won't get any light, they won't get any heat. And the sun would appear like a line in the sky instead of appearing like a circle. And it would appear like one really bright line in a very dark sky.
Okay.
Yeah.
Yes, another question from Tilak Sharma.
Yes, sir. So actually, it is a very great opportunity to be able to interact with you. So my question is, like, what are the factors that actually trigger the formation of sun flares and sunspots?
Oh, yeah. Okay. So flares and spots, very interesting. Actual factors nobody really knows. So we try to figure out what the real reason is. The more we try to understand these phenomena, the more problematic it gets. So some scientists several years back, they came up with the standard model of a solar flare. How a solar flare actually takes place. The interesting thing is, none of the solar flares follow the standard model of solar flare. Yeah, so every solar flare is unique. You don't see the standard model of solar flare out there. Yeah, so there are many things that really happen. So essentially, energetic activities, the magnetic field lines, the kind of magnetic field becomes very tightly concentrated in the sunspots, and because of that, you don't get much plasma in that region. It kind of repels all the plasma from there. Yeah, pushes everything around. It's like it's like a void. Because the magnetic field is so strong, it pushes all the plasma, it pushes all the gas, and that's why it appears very dark. And because the magnetic field is very strong, what happens is there's magnetic field from one region and magnetic field from another region. And these magnetic fields, they sometimes, with the movement of the sunspots, these magnetic fields just come close to each other and then they collide. And when these magnetic fields collide, it carries a lot of plasma from the bottom and it shoots it out in space. And it causes very, high brightness emissions. And some of the plasma goes out in space, what we call coronal mass ejections. And some of the plasma again falls down into the sun. And when it falls down with such high energy that part starts glowing in X-rays and all. Yeah. So there is a lot that happens during a solar flare. Yeah. And it's kind of like interchangeable effects. Sunspots causes solar flares cause sunspots, and then these cause CMEs, and then the solar flares are triggering CMEs, and CMEs are triggering solar flares, and then one solar flare happens that causes a lot of plasma interactions in a region that triggers another solar flare. All these things keep happening, and that's why I say that a solar flare is like a sunrise, because solar flares are common, just like sunrises are common. But like I said, every sunrise is unique. Same way, every solar flare is unique.
Ramaya Bhardwaj.
Sir, so my question was, so which kind of telescopes are used to see the sun?
Okay. So there can be a different types of telescopes. You could make a telescope at home and you could see the sun. Okay, but the thing is that you should be very careful while looking at the sun. If you're looking at the sun with your eye, first thing is, you should not look at the sun directly even without a telescope. If you're looking at the sun directly, don't look for more than 2 seconds or 3 seconds. Okay, look at the sky and then come down. But then if it's sunrise or sunset, it's absolutely safe. Yeah. If you can see the gola, if you can see the disk of the sun, then it's safe to look at the sun. If you can't see the disk of the sun, if it looks too bright, look away. Okay, 2 seconds to 3 seconds, not more than that. Then comes a telescope. So if you have a telescope, the first thing is you don't put your eye on the telescope and look at the sun, never. Yeah, that can cause irreversible damage. When you say that you can do operation and you can do eye replacement, that does not solve that problem, because it burns your retina. Your retina cannot be replaced. Okay, you will have permanent blindness in the center of your field of view. So never look at the sun directly. Other than that, there are many other methods, like there is pinhole camera method. Then there is telescope projection method. These are indirect methods. And then there are direct methods, like you use a solar filter in front of a telescope or in front of a binocular, but a safe solar filter, not with X-ray plate or with this what do you call this CD, floppy disk, hard disk. This is welder glass. Don't just take any welder glass. So you might find people saying you can use a welder glass to look at the sun. There is a specific number of welder glass, only that density welder glass you should use to look at the sun. And generally, I think that's generally such high intensity welder glass, welders also don't use. Yeah. So it's tough to find that welder glass also. So that's why, to look at the sun, the easiest method, if I tell you the easiest method is you take a piece of paper and punch a hole in it, which is maybe 5 millimeters wide. Okay. There are these punching machines. You take a piece of paper and then you punch 2 holes on the side. Yeah. You take that punching machine, you punch a hole in it, and then you hold it above your head and let the sunlight fall in the ground. You will see a circle. That's the best way to look at the sun. If there is a solar eclipse happening, you can see the shape of the solar eclipse with that. Okay.
One more question. So, curiosity, I wanted to ask if solar energy had any negative impact on the environment.
I didn't get your question. What is that?
Like, solar panels had a negative impact on the environment.
Yeah. Very good question. We always talk about how good solar panels are, but then we don't ask how solar panels could be bad. So let's say you have the state of Rajasthan. You have Jaisalmer, where you have lots of desert. Yeah. And you put solar panel all over Jaisalmer. Okay. If you put solar panel all over Jaisalmer, what will happen is all the heat will fall on the solar panel. Yeah. If all the heat falls on the solar panel, the snakes and the rats and the mice and these lizards that are staying inside the sand, who rely on the heat of the sand, they won't get any heat. No, they'll die. Right? Now, if you thought about a place where there is rainfall and you build solar panel over there. Now, when there is rainfall, all the water will go down, and you know that next day when the sun comes up, then that water will evaporate. But if you have covered with solar panel, that water will not get space to evaporate. It won't get any sunlight. So that place will become soggy. It will become like a marsh. Yeah. So these practical problems are there about solar flares, about these solar panels. Not only that, just think about it. If you put solar panels, let's say in a desert land or near a sea beach, the wind that was carrying the sand and that was causing see, how are sand dunes formed in a desert? Sand dunes are formed because the sand is carried by the wind. Now, if solar panels are covering all the sand dunes will never form. The sand will just stay still in one place. And if sand stays still in one place, and if sand becomes cold, slowly it will start becoming soil, because all these living creatures inside the soil will start dying. When they start dying, they'll start forming manure, and that will mix with the sand, and over hundreds of years, you will start seeing trees growing in a desert. Yeah. So all these things can happen. So solar panels, the effect of solar panels is not very drastic. So solar panels are not as unsafe as river taming projects where you put a dam, a check dam, or you put a big dam and you control the flow of the river. That affects life even more than solar panels. But then yes, solar panels can be bad under certain conditions. But that being said, there is a lot of research going on these materials called perovskites. So what they do is these are transparent solar panels. So the concept is you generate power using specific wavelengths of light, and you let every other wavelength go through. So you can make glass windows, and you can make glass doors, and you can make glass skylights, which are made up of these materials. So it will absorb, let's say, infrared, and it will absorb ultraviolet. It won't let those light come inside, but it will let visible light come inside. Yeah. So you have good illumination, but you also generate power.
Thanks for your patience, sir. We can come up with the last question. It's the longest session we had ever been at NASNI. So we can come with the last question from Anvika, I guess. Anvika, do you have any question?
Yes, ma'am, I have one.
Yes, you can ask.
Sir, have you ever seen Star Wars, the movie?
Absolutely, yeah, all of them.
So, sir, if it would be in the actual world, if there were two suns, what would we do? Like, would we survive?
Yeah, why not? If we are far away enough, if we are far enough from the star system, so that we can withstand the heat, then yeah, we can survive, and it'll be quite fun to have two suns. Yeah.
And sir, one more thing, that you said that nuclear fission happens over a million of years and then it comes out really fast. So, sir, what if the nuclear fission stopped, but it would still come, and for how much time would it come?
Okay. All right. So let's say the sun stopped doing this nuclear fusion reaction at its core. So for the next couple of thousands of years, we wouldn't know, because the sun will keep sending light. Because the light that is already trapped inside, that's still trying to come out. Only after several thousands of years would we realize, oh, the sun has stopped generating power. But there is one way of knowing if the fusion reaction is stopped or not. So there are these particles called neutrinos, which are formed during a fusion reaction. Yeah. So these neutrinos are what we call weakly interacting particles. They don't interact with anything. They just pass through. Yeah. So when we say they don't interact with anything, it means statistically, you should remember one thing. In science, there is nothing called impossible. Everything happens. You just have to have a huge statistic. So if you have billions and billions of neutrinos coming at you, then one or two of them will react with something or the other. That's why we have huge neutrino detectors. And there is also this detector called Ice Cube. You can look those up, which are made to detect these cosmological neutrinos and the solar neutrinos. So these neutrinos, they get detected, and as long as we are detecting them, we know that the fusion reaction is going on. So that's a very interesting thing, that when fusion happens, then the neutrino comes very fast. Neutrino comes at the speed of light, almost at the speed of light to us. So you get the neutrino of the fusion reaction that's happening now. But the light that you are getting is a couple of million years old. Okay. So if you stopped getting neutrinos, you would know, okay, the sun's core is not working anymore. But you can still be safe, because at least you and your next generation, at least 5 generations or 10 generations after you would would still keep getting the power from the sun.
Thank you so much, sir. It was a really inspiring session. And you started from God of Sun, and then you come up with these things that like solar flare, solar maxima, solar minima, plasma ball. It was a really an interesting session. I would ask Hemant sir to say a few words. Hemant sir, are you there?
Yes,
Tamanna
yes.
ma'am, I have one small question, if you would permit me.
Yes, madam. Amoli, ask your last question, please.
Yeah. Thank you, sir. Sir, recently we heard about a very large hole appearing on the surface of the sun. But when I look through my telescope, I don't see that. But it is visible in other frequencies. How and what is that?
Yeah, so these things are called coronal holes. So if you looked at this image, it looks kind of like this.
Yeah.
So these things happen because of open magnetic fields.
Okay.
So the magnetic field, since it's open, the plasma from there, it kind of, shoots out and goes into interplanetary space. And these magnetic fields, they recombine with other planets. Yeah. So the telescope that we use normally, that whatever we observe the photosphere of the sun.
Yeah.
The photosphere does not show signatures of these. So that if you looked at this, when you look through the telescope, the sun would appear like this, like on top. But if you observe the sun in extreme ultraviolet, that is lower corona, you would see that a part of the corona is missing. That's called the coronal hole. Now, the interesting thing is, if you look at photosphere, you won't see these. But if you look at photospheric magnetic field, if you could measure magnetic field on the photosphere, which there are instruments which use iron line to measure the magnetic field in the photosphere, you would see that there are more number of south poles than north poles, or there are more number of north poles than south poles. Now that's very interesting because magnets can always exist in dipoles. So if when you have a north pole, you should have a south pole. When you have south pole, you should have north pole. So ideally, to balance the total magnetic field of the sun, you should have same number of north poles than south poles. Yeah. But in coronal hole regions, we have seen that one pole dominates over the other. That's because there are lots of open field lines that kind of go out in space and then they recombine with magnetic fields of other planets.
Okay. Thank you, sir.
Thank you
I'll stay connected with you. Thank you, sir.
Absolutely.
Thank you, sir. Dr. Sarkar, you have given so much time with so much patience, and you have taken all the questions from the participants. And it was a very interactive and enlightening, because the more you know about sun and more curiosity comes to the participants. And I am happy that our students have asked so many questions, and lot more will be in their mind. Time is not permitting us to ask all the questions. So on behalf of NASNI and our senior members like Dr. Deka, Dr. Vandana Luthra, and our earlier um, speakers like Barua sir and Mangesh Sutar sir, they were also with us. And this session has been participated by all the segments of our audience. They were physicists, senior scientists, and astronomers, professional astronomers, and young enthusiasts also. So you have given a very knowledgeable talk. I'm very happy with this, and it is recorded and it will be shared with all the members, and it is also shared on IAPT website. So on behalf of NASNI and all the members, I thank you again very much for this session, and you have shared your knowledge with us. And hopefully we will be in touch, and we will have more talks, because L1, Aditya, and so many things are associated with your knowledge, and we will be happy to know more about it. And once again, thank you very much for today's session, and I thank all the participants, members to be with us in this session. And also thanks to Madam Tamanna. She hosted this this session today. Madam Amoli is here. She is always inspiring us with her, citizen science, and she has so many queries with all the members. And actually, her queries, gives us knowledge about all those topics also. So that is
really sorry to extend the session,
it's
sir.
not sorry.
I'm so sorry.
It is very exciting to know through you what you are doing and what are the new questions with you, and we get the answers from the experts. So thank you so much, all of you, and especially Dr. Sarkar. And I think now all the questions and there is no question in chat, and Dr. Deka has appreciated your talk, Dr. Sarkar, in the chat box. So thank you very much, and we now sign off this session and see you in next talk.
I have a video. If I can, let me check. If it's not, I'm not able to open it right now.
Thank you so much. I'm really, really honored to be invited here, and it
I
was.
have a doubt.
Akshay, we can take it later on. You can send me the doubt.
Take later on now. Now we sign off and see you all in next talk on first Wednesday of next month. Thank you very much and very good night. Thank you. Now we sign off.
Thank you, sir.
Thank you. Thank
I've
you.
left my email in the chat box. If anyone wants,
recording?
Yes, you can put, sir.
Yeah, I have put my email in the chat. So if anyone wants to ask anything later, you can feel free to write.
Right. Thank you so much.
Thank you session, sir.
Thank you so much.
On behalf of NASNI, we extend our heartfelt gratitude to you for sharing your expertise and passion with us. And it's a gentle reminder that our NASNI talks are held on first and third Wednesday of every month on this platform.
Yeah.
We look forward to your presence in the next session as well. Until then, keep looking up at the sky with wonder. Thank you and good evening to everyone.
Really, thank you so much.
Thank you.
Thank you.
Good night.
Bye, ma'am. Bye, ma'am.